Infinity does not erase our finiteness. It places it against a backdrop so wide, so quiet, that harshness softens, and what once felt final begins to feel like a turning of the page. It is also important to see that infinity is not always literal. Often it is a signal, a flare on the horizon, telling us that our maps have reached their edges. When Einstein's SIP's equations predict infinite density, it is not because nature loves infinities, but because our picture of nature is incomplete. When quantum theories spill infinite energies, it is not the world speaking, but our language breaking down. Infinity appears as a boundary, a signpost whispering, "The map ends here. The territory continues, still unexplored." Far from a flaw, this makes infinity a gift. It points the way to discovery. Even when it cannot be resolved, infinity inspires. It gives mathematics elegance. It gives physics puzzles. It gives philosophy riddles. It teaches patience, because no one ever conquers it. One can only live beside it, use it, respect it. It teaches perspective, because our small lives, finite though they are, take place in a universe with horizons that always recede. It teaches humility, because no matter how much we know, something vast awaits, beyond knowing. Perhaps its beauty lies exactly in the fact that it cannot be contained. Infinity will never be reduced to a single number, a single theory, a single word. It is not a destination. It is a horizon, always shifting, always ahead. The more we learn, the more it stretches, and that is not failure. That is the point. Infinity ensures that curiosity never ends. There will always be more to see, more to ask, more to imagine, more to wonder about. In the quiet of night, beneath a sky scattered with stars, infinity is not frightening. It is serene. It stretches without sound, a canvas too wide to ever be filled. And in that vastness, our brief sparks of life find meaning. We do not need to hold infinity whole. It is enough to know it exists. Enough to know that reality is larger than us, larger than our worries, larger than any boundary the mind can draw. That knowledge brings peace. A peace made of continuity, depth, and beauty without measure. Infinity, then, is not a problem to solve, but a companion to live with. It is the quiet assurance that there is always more. More time, more space, more questions, more mystery. It is the endless backdrop against which our finite stories unfold. To meet infinity is to remember that life itself is a brief spark inside the boundless, and that spark burns brighter because the night around it has no end. So, as this journey closes, it does not truly end. Infinity does not allow endings. The numbers will keep rising. The horizons will keep stretching. The riddles will keep deepening. And that, in the hush of it all, is the beauty of the endless. The goal is not to conquer infinity, but to walk beside it, to let it remind us that there is always more, and in that reminder lies a quiet hope. For as long as infinity remains, so too does the invitation to wonder, to imagine, to reach gently outward, toward the endless. These paradoxes unsettle because they resist resolution. They tease logic. They mock common sense. And yet, they also delight because they stretch imagination, remind us that reason itself has edges worth leaning against. Infinity is not here to be solved. Once and for all, it is here to be lived with, like a horizon that recedes the closer we approach. Its beauty is not in closure, but in the pursuit, in the way it keeps us moving, ever outward, ever onward. Perhaps the most calming aspect of infinity is its ability to soften the sharpness of finality. Endings in human life are abrupt, unforgiving, the final breath, the closing of a book, the last sound of a song. These are boundaries we cannot step around. Infinity, by contrast, whispers of continuities. It reminds us that on scales beyond our own, there may be no hard stop. Space may keep flowing, time may keep unfolding, possibility may keep blooming. Without closure, even if our lives are finite, they unfold within a mystery that does not end. That thought can soothe a strange peace, a reassurance that existence itself is not as fragile as the fleeting moments we live inside it. Infinity, then, is a paradox not only of numbers, but of feelings. It terrifies with enormity. It comforts with continuity. It puzzles with contradictions. It inspires with scope. It is both beyond comprehension and intimately woven into daily life. From the simple act of counting to the dizzying vastness of the night sky, its beauty lies in duality, both challenge and consolation, both the sharp edge of mystery and the soft curve of wonder. To contemplate infinity is to be stretched. We cannot contain it, but we can let it shape us, as thinkers, as dreamers, as finite beings who glimpse the boundless. And in that glimpse, we discover something, not only about the universe, but about ourselves, that our curiosity, like infinity itself, has no end. It spills over, slipping beyond what we see day to day, beyond errands, beyond routines, into the wide silence that hums underneath everything. What is striking is that infinity does not belong to just one corner of thought. It is not confined, not fenced in. It appears everywhere. The mathematician feels it, in endless sequences, in sums that never close, in sets too large to be counted. The philosopher meets it in infinite regress, in questions that always require another answer behind the answer, in time imagined without beginning and without end. The physicist encounters it in singularities, in horizons that cannot be crossed, in theories that collapse under their own weight, when infinity creeps in. And the poet, the artist, the dreamer, they glimpse it in softer ways, in the sky that stretches without boundary, in the river that seems to flow forever, in the boundlessness of love, in the endless rooms of imagination. Each discipline, each perspective, circles the same vastness, never catching it, never holding it still, always aware that it stretches just beyond the fingertips. Infinity is also a mirror of our own limits. We are finite creatures. Our lives span a handful of decades. Our eyes catch only a sliver of light. Our ears hear only a narrow range of sound. Our minds evolved to count sheep, to track seasons, to gather fruit, not to wrestle with the endless. And yet, we reach, we stretch, we lift our gaze. That reaching is what defines us. We may never hold infinity whole, but the act of trying is one of the purest expressions of human curiosity. To chase infinity is to confess that knowledge is incomplete, but it is also to affirm that knowledge can keep growing without boundary. A river of thought that never dries, always flowing, always carving new paths. There is humility in standing before infinity. The observable universe already dwarfs us, billions upon billions of galaxies, each one thick with stars, and beyond the visible bubble may lie stretches without end, oceans of light we will never see. Time itself may flow so far ahead that even black holes evaporate into whispers, that even the densest stars fade into quiet dust. At the smallest scales, space and time may dissolve into trembling depths, where the ordinary rules cease to apply. Infinity towers over us, from every direction, above, below, within. And yet, instead of crushing us, it enlarges our wonder. It makes our questions bigger, our imagination wider. To know we are finite is also to know that we live inside something immeasurably greater. Infinity also softens perspective. Endings in daily life feel so sharp. The end of a story, the end of a day, the end of a life. But infinity whispers, perhaps endings are not absolute. Perhaps time continues. Perhaps space keeps stretching. Perhaps possibilities unfold beyond sight. Our own part may be brief, but the stage is vast. Infinity is a word with two faces. One face unsettles, equations collapsing into nonsense, futures stretching into endless cold, the abyss of the unknowable. The other face comforts, continuity without end, a story that never truly closes, an embrace that softens the fear of endings. It is both abyss and cradle, terror and solace, mystery and reassurance, woven together as finite beings, fragile and brief. We feel both awe and unease when we look into the endless. Infinity overwhelms, yet it also soothes. It makes us dizzy, and it steadies us. Beneath the night sky, already speckled with countless suns, we sense it. Stars upon stars, galaxies beyond galaxies, horizons stretching into more horizons. The mind strains, the heart trembles. To picture it all, without boundary, is to feel small, so small that the self nearly dissolves. For some, this is frightening, a sense of being lost, of vanishing into something too vast. But for others, the same vision is balm. Infinity means there is no final wall, no terminal silence, no ultimate edge where the story stops. Time without end can be daunting, yes, but it also whispers continuity, a gentle promise that whatever ends, something else will go on, just as the sea does not halt at the horizon, but keeps flowing. Beyond sight, infinity reminds us that reality is always larger than our fears. When we think about meaning, when we hold our brief lives against the backdrop of the endless, we feel a peculiar tension. A finite life, within an infinite universe, can appear insignificant, like a single grain of sand, on a beach without end, drowned among trillions. And yet, paradoxically, that same grain can shine, all the brighter for its smallness. The brevity of our moments makes them glow, a flame flickering, more precious for being fragile. Infinity provides the context, but finiteness gives the weight. without the endless, we would not feel the bittersweet sharpness of the fleeting. Without the finite, the endless would mean nothing. In this way, infinity frames our experience, reminding us that our tiny span is not isolated, but woven into something immeasurably vast. For many traditions, infinity carries a spiritual resonance. It has been used to describe the divine, the eternal, the ungraspable presence that surpasses all measure. Philosophers and poets have long invoked it, not as an equation, but as a symbol of love without boundary, of wisdom that spills over edges, of beauty that refuses confinement. Even outside of religion, infinity continues to serve as a metaphor of transcendence, a concept that lifts the mind above the ordinary day, above the confines of time and space, into the wide hush of the immeasurable. To call something infinite is to acknowledge its refusal to be pinned down, its power to stretch beyond every wall we raise. And there is something deeply human in our ability to imagine infinity at all. No other creature, as far as we know, pauses to wonder whether time has an edge or whether space ends. Birds migrate by instinct, but they do not ask if the sky itself has a boundary. Ants move in endless lines, but they do not puzzle over infinite regress. Humans alone carry this burden and this gift, the ability to conceive what has no conclusion, to dream of what extends forever, to imagine the impossible without flinching. That very act of imagining is a kind of beauty in itself. It shows that thought can wander past fences, that imagination is unafraid to stare into the endless and call it by name. Infinity also bridges the world of science and the world of art. In equations, it sharpens predictions. It gives calculus its power, lets infinite sums collapse into precise answers. In poetry, it becomes metaphor, a symbol of unbounded longing, a gesture toward the vast. A mathematician may write of infinite series, while a poet writes of infinite desire. Different languages, but both circling the same shadow of meaning. Music too brushes the infinite, repeating motifs, echoes without conclusion, loops that refuse to end. They give the listener a sense of stretching beyond time itself. One line of notes, played again and again, becomes not repetition, but eternity. The arts remind us that infinity is not only something to calculate, but something to feel. Not just a riddle, but a canvas for emotion. Even paradoxes carry a strange beauty. Zeno's puzzles show us that walking across a room can contain infinite steps. Hilbert Sepp's hotel shows us that fullness can still hold more. The idea of a multiverse suggests that our own world may be only one among countless others. Some proposals suggest that the singularity itself is not an end, not an infinite collapse, but a veil. Behind the veil, quantum effects stir. They replace the impossible point of infinite density with a finite region, a place where space and time themselves quiver, fold, and rebound. In such views, the heart of a black hole is not a bottomless well, but a bounce, a hidden passage where gravity Sepp's crushing grip is softened by the granularity of the quantum. The same possibility spreads back into the beginning. Perhaps the Big Bang was not the first page, but a turning one, a transition from an earlier universe, with quantum laws smoothing out what relativity renders impossible. But infinities do more than whisper about black holes and beginnings. They raise stubborn questions about what is real and what is artifact. Take the vacuum. Quantum field theory predicts that even the emptiest space teems with energy, an infinite sea, a restless froth. Yet in daily life, we do not feel crushed by infinite energy pressing down. This mismatch between the predicted vacuum energy and the measured faint push of dark energy is staggering. The so-called cosmological constant problem is not a small discrepancy. It is an abyss, a gulf so vast that it signals something fundamental has been misunderstood. Here, infinity does not illuminate. It blinds. It tells us, loudly, that our theories, be resilient as they are, cannot yet be the full story. There is another reason physicists eye infinity with suspicion. It erodes clarity. It dilutes meaning. When a theory allows infinity freely, almost anything can be explained. And in explaining everything, it explains nothing. Predictions dissolve. Falsifiability fades. Theories become shelters for confusion, walls of endlessness that hide rather than reveal. So infinity must be constrained, tamed, treated with suspicion. It is not to be banished, for it still teaches, but to be watched carefully, like a fire that both warms and burns. And yet, even in suspicion, there is humility. Infinity is not an enemy. It is a teacher. Each time it erupts in our equations, it points to a crack, a border, a place where our knowledge slips into the unknown. Black holes, the Big Bang, the structure of space-time itself. At each of these edges, infinity stands, like a silent guidepost, whispering, "Look deeper. Do not stop here. The truth lies beyond." Far from useless, infinities are luminous markers, guiding us toward the limits of our understanding. They tell us where the map ends and where the next map has yet to be drawn. The search for deeper theories, in many ways, is a search for a universe without infinities, or at least one where infinities are understood, absorbed, made gentle, strings, loops, or something not yet imagined. Whichever path proves true, the goal is the same: to describe reality without collapsing into the endless. Until then, physicists walk carefully. They treat infinities as warnings, as signs to tread lightly. For infinity is not a measurement. It is not a state. It is a horizon of thought, a line at which our finite minds and fragile equations press too hard against the whole of reality. When physics breaks under infinity, it is not the universe failing us. It is our models, our maps, our scaffolds of reason, revealing their limits. And in those cracks, illuminated by the glare of infinity, new theories are waiting, quiet, like seeds, under the soil of understanding. At the heart of a black hole, relativity insists that matter collapses into a point of infinite compression. At the dawn of the cosmos, it shows us a beginning of infinite heat, infinite density, the Big Bang as singularity. But these infinities are not triumphs. They are cracks. They are signs that relativity, for all its brilliance, is incomplete. Quantum field theory, the proud jewel of modern physics, has its own brush with infinity. When physicists calculate the interactions of particles, the numbers often explode. The self-energy of an electron, for example, its own field feeding back into itself, comes out infinite if calculated naively. Left alone, the predictions would collapse. So physicists invented a delicate maneuver, renormalization. By redefining certain quantities, they sweep the infinities aside, taming them, replacing nonsense with numbers that match experiments to dazzling accuracy. Better than 1 part in 10 billion. It works. It works almost too well. And yet, there is unease. Renormalization feels, to some, like sweeping dust under the rug. The house looks spotless, but the dust remains. The infinities whisper still. The deepest clash, however, comes when relativity and quantum theory are forced into the same room, separately. They are brilliant. Relativity rules the vastness, the stars, the galaxies. Quantum mechanics rules the small, the atoms, the particles. But when they meet, when gravity and quantum effects both demand attention, the mathematics explodes. Infinities proliferate, not tame, not renormalizable, but wild, out of control. Black hole singularities, the Big Bang itself. These are arenas where both theories must act, and both fail. Here, infinity is not tool or guide, but barrier. Cosmology adds more unease. If space is infinite, then matter and energy are infinite too. How do you assign probability in such a landscape? How do you say this event is likely when both it and its alternatives occur infinitely many times? Eternal inflation, the idea of universes bubbling without end, makes the problem sharper still. Physicists call it the measure problem. An infinite set defies comparison. Without a way to weigh it, prediction itself begins to dissolve. This is why physicists distrust infinity. Not because they dislike vastness, not because large numbers scare them, but because infinity in an equation usually means the map has ended. It is as though a cartographer, drawing coastlines with care, suddenly extends their ink into the ocean, and instead of neat lines, nonsense fills the page. Infinity, in physics, is a sign, not here, not yet. Something deeper waits. And so, the search for deeper theories begins. One path is string theory. Here, the point-like particles of old are replaced with tiny vibrating strings. By giving particles a finite size, strings smear out the infinities. They prevent densities from collapsing to zero size. They soften singularities, turning impossible infinities into manageable finiteness. Another path is loop quantum gravity. It imagines space-time, woven of tiny loops, discrete grains of geometry, no longer infinitely divisible, but pixelated at the Planck scale. Here, singularities dissolve. Curvature does not climb to infinity, but plateaus. The Big Bang becomes not a singular beginning, but perhaps a bounce, a passage from one phase of cosmos to another. Hints abound in black hole models, in cosmological equations, that infinities, once feared as unscalable walls, may dissolve under the gentler light of a deeper theory. This puzzle, known as Olbers's paradox, troubled astronomers for centuries. The resolution lies in the youth of the cosmos and its restless expansion. Starlight from distant galaxies has not yet arrived. Other light is stretched into invisibility as the universe races outward. Still, the paradox lingers as a reminder. Infinity is not just abstract. It touches what we see. It seeps into observation. Even probability feels the sting of infinity. Flip a fair coin forever, and every sequence appears. 1,000 heads in a row, a perfect alternation. Every pattern conceivable. Infinity ensures that randomness and certainty blur together. What is rare becomes inevitable. And here again, the paradox brushes against the multiverse. If reality offers infinite trials, then everything permitted by the rules must eventually happen. Every story, every possibility, every strange and impossible scene is realized somewhere, sometime. Infinity, then, is not gentle. It is not polite. It disrupts. It bends reason. It unsettles intuition. And yet, in its disruptive wake, it leaves gifts. Zeno sips puzzles, planted the seeds of calculus. Hilbert Sepp's Hotel clarified the logic of infinite sets, infinite regress, pushed philosophers toward deeper reflections. Cosmic paradoxes sharpened astronomy. Infinity unsettles, and in unsettling, it teaches. Its riddles have driven progress, as much as they have sown confusion. Perhaps, then, paradox is the natural language of infinity, its way of speaking to us. When we step into the endless, we leave behind the familiar grammar of the finite, full and empty, near and far, before and after, cause and effect, all buckle, all falter, under the weight of the infinite. Infinity does not break. It is our tools that do. The human mind is built for edges, for beginnings and endings, for the relief of boundaries. Yet infinity offers neither. It is a mirror that reflects the limits of thought itself, always handing back a riddle when we expected an answer. But paradox is not only nuisance, it is also a lantern. To confront it is to glimpse the strangeness of reality, to sense how wide the universe might truly be. Infinity forces us to think differently. It unsettles certainty, but it fertilizes imagination. In the infinite, answers are rare, but wonder is abundant. The riddles of infinity are not locked doors, but open windows. Through them pours the strange, the beautiful, the uncontainable light of the endless. Physicists, however, hold an uneasy truce with infinity. Mathematicians may play with it, build frameworks around it, treat it like a loyal companion. But in physics, infinity is often the signal of something gone wrong. It creeps into equations like an uninvited guest, and when it appears, it whispers not revelation, but breakdown. In the physical world, nothing we know is truly infinite. Not energy, not density, not curvature. So when infinity arises in the mathematics, it is not truth, but warning, a red flag that our description has outlived its domain. Einstein sips general relativity, makes this tension vivid. The theory is elegant, astonishing, a reshaping of gravity itself, from force into geometry. It shows how matter and energy bend the fabric of space-time, how planets trace graceful curves around the sun, how light itself can be bent into arcs. It explains orbits, predicts expansion, and has been tested again and again. with exquisite precision, and yet, hidden in its equations, are singularities, points where density and curvature become infinite. His puzzles are not proofs against movement, but signposts, strange and glowing markers pointing toward the complications that infinity always brings, and in time, mathematics learned to soothe these paradoxes. The key was found in the language of convergent series. Consider the infinite sum. Nesja sudlu funduri. It seems endless. It feels like a staircase that will never end. But the sequence does not spiral out forever. Instead, it leans closer and closer to a boundary. It approaches one. In this way, Achilles does overtake the tortoise. The infinite steps he must run take only a finite time. The chase resolves, and yet, even with resolution, Zeno sips paradoxes whisper unease. They remind us that infinity is never far away, lurking even in the simplest act of walking across a room. Centuries later, another paradox emerged. This time, it was not born from the sands of Greece, but from the imagination of the mathematician, David Hilbert. He dreamed of a hotel not of 100 rooms, nor 1,000, nor even 1,000,000, but a hotel with infinitely many rooms, and in this hotel, every room is filled, completely occupied, a full house. At first glance, it seems there is no space for new guests, but infinity has other plans. If one more traveller arrives, the manager smiles. They simply ask the guest in room 1 to move to room 2, the guest in room 2 to move to room 3, and so on, forever down the hallway, without end. And suddenly, room 1 is free. The hotel was full, yet it has made space. The strangeness deepens. Suppose an infinite bus arrives, doors swinging open, to release infinitely many new guests. Still, Hilbert Sepp's hotel finds a way. Each current guest is asked to double their room number. From room no to room 2, n, every odd-numbered room is now vacant, and into those infinitely many openings pour the infinite travellers. The impossible becomes possible. A hotel both full and open. A paradox of welcome. Hilbert Sepp's hotel reveals how infinity resists the ordinary logic of numbers. A set can be complete and still have room for more. Subtract infinitely many occupants, and still infinitely many remain. Infinity is elastic, stretching, contracting, twisting itself, beyond the arithmetic of the finite. And these paradoxes, strange though they feel, are not errors. They are glimpses of how infinity truly behaves. Philosophy, too, has its own infinities to untangle. Consider infinite regress, a chain of causes, with no first link. If every effect requires a cause, then every cause must itself be caused, and on, and on, and on, backward without end. How can a chain, with no anchor, ever hold? Aristotle wrestled with this. Medieval theologians wrestled with it too. Their answer: an uncaused cause, often identified as God. Yet philosophy never fully escaped the puzzle. Infinite regress also stalks the territory of knowledge. If every belief must be justified by another belief, and each justification demands its own foundation, then the chain stretches endlessly. Do we ground knowledge on self-evident truths, Or do we wander endlessly, climbing a staircase without a bottom step? Here, infinity becomes a trap, a hall of mirrors with no exit. Cosmology inherits its own riddles of infinity. Imagine an eternal past, a universe without beginning. If time stretches backward forever, then an infinite number of moments has already passed. But if infinity has already unfolded, how could we ever arrive at now? It is like climbing a ladder with infinitely many rungs below. No matter how high you climb, the top always recedes. This thought pushes many cosmologists toward a beginning, a big bang, a first moment, a point of origin. And then comes another riddle, the night sky itself. If the universe is infinite, and stars are scattered without end, then in every direction you look, your gaze must eventually fall upon a star. The sky should blaze with unbroken light, a ceiling of fire. And yet, the night is dark. Infinity does not live in a single place. In the brain, it arises as a chorus. It emerges as a collaboration, a weaving together of circuits for numbers, for imagination, for metaphor. To think about infinity, the brain must build bridges out of many tools lashed together, each one fragile on its own, but in combination strong enough to step, tentatively, toward the endless. This raises a question. Do we need to understand infinity to use it? The answer, it seems, is no. Humanity has built mathematics, astronomy, physics, all resting on the idea of infinity, and yet no one truly comprehends it, in all its strangeness. But this is not unusual. We use quantum mechanics too, a framework that no one fully understands. In an intuitive sense, the mind manages by symbols, by rules, by careful logic. It pushes imagination just far enough to make predictions, to find patterns, to carve results out of the infinite mist. Infinity, then, is less something we hold and more something we orbit. We circle it endlessly, with equations, with metaphors, with stories, with myths. And here lies something remarkable. Infinity reveals the unique power of human imagination. Our ancestors did not need infinity to survive, to hunt, to gather, to plant and harvest. Endlessness was unnecessary. Yet somewhere, beneath the stars, human beings began to wander. They saw the heavens without number. They imagined days without end. They discovered numbers that never stopped rising. Infinity became a symbol of the restlessness of the mind, its refusal to stop at the visible and measurable, its hunger for the beyond. Perhaps this is the deepest truth. We may never hold infinity entirely within thought, but in striving to, we discover the creativity and flexibility of the mind itself. Mathematics turns infinity into a tool. Metaphor makes it vivid. Imagination makes it playful. And so the brain does not wrestle with infinity to conquer it. It wrestles with it to learn from the struggle. Each failed attempt to hold the endless directly leaves behind something new, a discovery, a work of art, a poem, a paradox, a question that deepens us. Infinity, in the end, is not just out there, in the cosmos, in equations, in the endless scatter of stars. It is also inside us, in the way thought expands, in the way memory stretches and collapses, in the way imagination leaps beyond survival. The human mind cannot contain infinity, but it can dance with it, and that dance is one of the most remarkable achievements our species has ever made. And yet, infinity does not come gently. It leaves riddles. It leaves paradoxes. Every time we think we've captured it, it slips away. A horizon always retreating, a puzzle maker, more than a solution. From the first philosophers to the latest cosmologists, infinity has created questions that bend reason, confound intuition, and challenge even the most patient thinker. One of the earliest explorers was Zeno of Elea, a Greek philosopher of the 5th century BCE. His paradoxes endure because they are simple but devastating. Take the dichotomy paradox. To walk across a room, you must first cross half the distance. Before that, you must cross half of that half, and before that, half of the half of the half. This halving continues endlessly, an infinite series of steps. If you must complete an infinite number of steps to arrive at the other side, how do you ever arrive? Or consider Achilles and the tortoise. Achilles, swiftest of the Greeks, races a tortoise. The tortoise is slow, but is given a head start. By the time Achilles reaches the tortoise's starting point, the tortoise has moved on, just a little ahead. Each time Achilles reaches where the tortoise once was, the tortoise has advanced again. The chase never ends. The gap never closes. Achilles never overtakes. Of course, in the real world, Achilles speeds past in moments, but Zeno's paradox lingers, a reminder of the tension between infinite divisibility and the flow of motion, the eternal, the divine, the infinite mind of God. To call something infinite is to grant it a quality of ultimate otherness, a scope beyond human limitation. In these contexts, infinity becomes not something to calculate, but something to contemplate, a way to point toward transcendence. Mathematics, however, offers a more disciplined bridge. The invention of calculus showed how infinities can be tamed into tools. By working with limits, mathematicians discovered that processes which never end can still yield precise answers. An infinite sum of fractions can converge to a finite result. An infinitely small slice of time can help us measure velocity. The brain does not need to picture infinity directly. It only needs to manipulate it through symbol and reason. And so, humanity has harnessed infinity to build bridges, to send spacecraft across the solar system, to design the electronics that shape our world. Infinity, though unseen, is everywhere in the mathematics of modern life. Imagination, too, plays its part. Writers and philosophers have long used infinity to test the limits of thought. Jorge Luis Borges spoke of infinite libraries, endless books, mazes that loop without end. Douglas Hofstadter explored infinity through recursion, through self-reference, through patterns that fold back on themselves in endless descent. These thought experiments do not solve infinity, but they make it vivid. They haunt the mind. They keep the idea alive in culture, in literature, in art. There is even a curious connection between infinity and human memory. No one can recall an infinite sequence of experiences, and yet the mind compresses and stretches time. A single moment can feel endless, like waiting in silence like standing in awe, like drifting into sleep. Entire years can collapse into the blink of an eye, remembered as if they were nothing at all. The mind cannot hold infinity, but it can taste it. It can brush against it in moments that swell and stretch, as though time itself is pausing to take a deeper breath. It can graze the endless in memories that collapse inward, vanishing in a flash of recollection, compressing years into seconds, collapsing lifetimes into the span of a single thought. In this way, the brain generates its own illusions of infinity, stretching experiences until they feel timeless, spiraling loops of thought that circle endlessly inward, like whirlpools in the stream of awareness. This subjective infinity is not mathematical. It is not cosmic. It is psychological, another fragile, flickering way in which the mind brushes against the boundless. Philosophers have long wondered whether the mind can ever truly grasp infinity. Immanuel Kant suggested that infinity is not something we perceive with the senses. We cannot touch it, or see it, or measure it directly. Instead, it is an idea of reason, a construct of the mind, something we frame, something we circle, something we reason about, but never hold in full. And in this way, infinity becomes a mirror for the mind itself, always reaching, always stretching, always leaning just beyond its limits. Interestingly, neuroscience whispers that even the brain SIP's architecture betrays its struggle with the endless. When we deal with small numbers, specific regions of the parietal lobe spark and glow with activity. But when we stretch toward very large numbers, toward magnitudes without end, different circuits stir, as if the brain itself must recruit new strategies for the boundless. The multiverse reflects our longing to imagine beyond the single thread of history we are given, and yet, at the same time, it reminds us that the thread we do inhabit is unique, even if countless variations exist. This moment, this particular unfolding, is ours. Infinity does not diminish it. It heightens its preciousness. Whether or not other worlds are real, the fact that we can conceive of them reveals the power of imagination, a spark lit by the idea of the endless. In the end, the multiverse may remain unproven, a vast speculation, forever beyond confirmation. Or, perhaps, it will turn out to be real, with evidence waiting quietly, hidden in the background of the cosmos, waiting in the faint scars of ancient light, waiting in the mathematics of theories, yet to be born. Either way, the very thought of it widens our horizon. It stretches the boundaries of the possible, and it draws us once again to the brink of infinity, to gaze into its endlessness, with a mixture of awe and wonder. The notion of parallel worlds embodies the very essence of infinity, the idea that reality is always larger than any single version, any single history, any single possibility. Infinity may not guarantee that everything happens, but it guarantees this, that wonder will never run out. Infinity is everywhere in human thought, and yet it never quite fits comfortably in the mind. We can say the word easily enough. We can sketch the sideways figure 8. We can describe something as going on forever. But when asked to picture it, the imagination falters. The mind stumbles. The brain, so good at counting steps, measuring days, holding beginnings and endings, strains against a concept that has no end at all. To grasp infinity is to stretch beyond the architecture of our own neurons. And yet, again and again, humanity has reached for it. Through mathematics, through metaphor, through imagination, through faith, through art. Even children encounter infinity early. It often begins as a counting game. A child might announce, proudly, "I can count to the biggest number," only to be gently told that no matter how high they count, there is always one more. This discovery is thrilling and unsettling. Numbers never stop. Soon after, many children invent their own idea of infinity, not as an endless process, but as the biggest number of all, a trump card, a mountaintop, the ultimate answer. Of course, mathematicians later explain that infinity is not a number at all. It is not something you reach, or contain, or climb to the top of. It is a concept, a direction without limit, a horizon you can approach, but never arrive at. Still, the instinct is natural. The mind longs to contain the uncontainable. And even the adult mind does not escape this tension. Trained mathematicians, with all their skill and rigor, acknowledge that infinity is not something tangible. It is a tool, a framework, a way of thinking that bends beyond intuition. The discovery of multiple infinities by Georg Cantor stretches this even further. It is one thing to imagine endlessness. It is another to imagine infinities larger than other infinities. Cantor himself once described the journey into transfinite numbers as walking through a strange landscape where all familiar landmarks had vanished. For most of us, the only way to cope with infinity is symbolic. We do not truly picture it. We learn its rules. We treat it carefully. We handle it with logic and symbols, like delicate glass. Psychologists who study the human brain find that our minds are tuned for magnitude, but not for infinity. We can grasp more and less. We can estimate large quantities. We can count far beyond what we actually need in daily life. But at some point, the difference between 10 trillion and 100 trillion slips away. It becomes meaningless to intuition. Infinity lies forever outside that zone. No matter how far you climb, it is always further still. So when we think of it, we reach for metaphor, the endless road, the boundless ocean, the unbroken horizon, the night sky. All these images help carry the weight of the idea, even though in reality, all of them are finite. Religions and philosophies have long used such metaphors to approach infinity. There is a universe where dinosaurs never went extinct, another where humanity never evolved, another where you made a single different choice on an ordinary morning and set your life on a new path. There may even be universes where the laws of physics differ so completely that life itself takes forms we cannot even imagine. Infinity, in this context, is not only endless time, not only endless space, but endless possibility. A canvas without borders, a stage without curtains, copies, yes, but also endless creativity. Not mere repetition, but a boundless gallery of realities being painted all at once. But does infinity truly guarantee everything? The answer depends on what kind of infinity we are speaking of. If space is infinite, yet ruled everywhere by the same physical laws, then only the possibilities, allowed by those laws, will unfold. You may find endless earths, endless suns, endless histories repeating, with only slight variations. But you will not find a universe where 2 plus 2 equals 5, or where contradictions hold. Mathematical truth remains a backbone even across infinity. But if the multiverse includes not just endless space, but different laws themselves, different constants, different foundations, then the scope of possibility grows enormously. Perhaps then, almost anything conceivable could exist somewhere. A cosmos where stars never form, another where gravity is stronger than light, another where consciousness blooms in shapes we could not recognize as alive. Even so, not every dream is realized. Not every story the imagination spins is physically meaningful. Infinity opens many doors, but not all of them. One common objection to the multiverse is that it may be untestable. If other universes exist, but are forever sealed off from us, beyond every telescope, beyond every experiment, how can we ever know? Some physicists say this makes the multiverse a philosophical idea rather than a scientific one, since science depends on observation, on falsifiability. Others reply that even if we cannot see these other worlds directly, their existence may leave whispers behind. If our bubble universe once collided with another during inflation, it might have left faint scars, subtle ripples, in the cosmic microwave background, patterns waiting to be found. And so the search continues. Evidence may be faint, but the possibility remains alive. Even without proof, the multiverse carries a certain explanatory power. One of the deepest puzzles in physics is why the constants of nature seem so finely tuned for life. The strength of gravity, the charge of the electron, the expansion rate of the universe. Change these values only slightly, and stars would never ignite. Atoms would never bind. Life as we know it would be impossible. If there is only one universe, then this fine-tuning is an astonishing coincidence, a mystery begging for an answer. But if there are infinitely many universes, each with different constants, then it is not surprising at all. Life arises only in the rare pockets where conditions permit it, and observers, like us, naturally find themselves in such places. This is the anthropic principle. Infinity turns coincidence into inevitability, yet infinity does not come without paradox. If there are infinitely many universes, how do we assign probabilities? How do we say one outcome is more likely than another when both occur infinitely often? This is the measure problem of the multiverse. Almost everything that can happen will happen infinitely many times. Distinguishing meaningful predictions from noise becomes a delicate, slippery art. Infinity makes possibility boundless, but also unstable, like trying to weigh clouds. For all the debates, the idea of parallel worlds remains one of the most captivating offspring of infinity. It has haunted human imagination for centuries. From ancient speculation about countless worlds to modern science fiction tales of alternate histories and mirror selves, the difference today is that these ideas are no longer just myths or stories. They stand at the edge of serious physics, cosmology, inflation, quantum mechanics, all whisper hints that reality may be broader than what we see. There is also a deeply human element to the fascination with parallel worlds. Who has not wondered what life might be like if they had made a different choice, if they had taken another path, if they had been born in another time Another place, under another sky, the multiverse, whether real or not, offers a stage for those questions to play out on an infinite scale. Somewhere, perhaps, there is another version of you, living that alternative life. Somewhere, perhaps, another version of humanity faced its trials differently and built a world unlike ours. What unites all these speculations is the recognition that infinity is both a tool and a warning. When equations predict infinite density, as in the Big Crunch, it signals that our theories are incomplete. When entropy stretches into infinite time, as in the heat death, it reveals the limits of human imagination. When numbers grow too large to picture, when expansion accelerates toward infinity, as in the Big Rip, it challenges our assumptions about stability itself. Infinity is never just a number. It is a horizon, a cliff edge, a boundary where physics brushes against the unknowable. For human beings, these endings are both terrifying and strangely calming. Terrifying because they remind us of the fragility of everything we know, our stars, our world, even the fabric of space-time itself. But calming because they are so distant, so immeasurably far in the future, that they feel more like stories than threats. The heat death will not trouble anyone alive today, nor their children, nor their descendants for countless generations. The Big Rip, if it ever comes, lies billions of years ahead. The Big Crunch, if it is real, would take even longer. Infinity itself softens fear. By sheer scale, it places our lives into perspective against the endless ocean of cosmic time. So how will the universe end? The truth is simple. We do not know. Each theory carries its own infinities, its own flavor of the endless. Perhaps the cosmos will collapse. Perhaps it will drift forever. Perhaps it will tear itself apart. Or perhaps there is an ending we have not yet imagined, waiting quietly, beyond the reach of our current theories. What is certain is this: infinity will be there, woven into the finale of the grandest story we know, whether as density, whether as time, whether as expansion. The universe seems destined to embrace the infinite in its last breath. Infinity also inspires one of the most provocative questions in science and philosophy. If the universe itself is infinite, does that mean every possible event happens somewhere? Does infinity guarantee that there are endless versions of you, living out endless variations of your life across a vast cosmic patchwork? This is the allure of the multiverse, an idea that stretches imagination as far as the observable universe, and then keeps going. The multiverse is not a single theory, but a family of possibilities. One of the simplest arises from the idea of infinite space. If space truly stretches on without bound, then matter must be arranged in countless different ways, and because there are only a finite number of possible arrangements within any given region, those arrangements must eventually repeat. In an infinite cosmos, there could be regions unimaginably far away that look exactly like ours: another Earth, another sun, another you, sitting in another room, listening to this very story. The odds of this happening nearby are impossibly small, but across infinity, the improbable becomes inevitable. Another pathway to the multiverse comes from cosmology and the idea of eternal inflation. Inflation, that brief, rapid ballooning of space in the first instant after the Big Bang, explains many of the large-scale features we see today. But in many models, inflation never ends everywhere at once. It ends in some regions, while continuing elsewhere. Each region where inflation stops becomes a bubble universe, like our own. Each bubble can carry its own physics, its own constants of nature, perhaps even its own dimensions. The result is a cosmic froth, a foam of universes, each one unique. Here, infinity is not just repetition of the same, it is variation without limit. Quantum mechanics adds its own twist, with the many worlds interpretation. In this view, every time a quantum event has multiple possible outcomes, the universe branches. One version of you sees the coinland heads, another sees tails. The superposition of states never collapses. Instead, reality itself splits, over and over, spawning an infinity of parallel histories. Whether or not this interpretation is true remains a matter of fierce debate, but it demonstrates, once again, how infinity creeps into the structure of possibility itself. The philosophical consequences are enormous. If there are infinitely many universes, then every possible history is played out somewhere. Space itself would collapse. Time itself would buckle. The big crunch is the cosmos, folding back into itself, a grand return to a singular point. Though current evidence, the accelerating expansion driven by dark energy, makes this fate seem unlikely, the big crunch still holds a certain poetry, infinity at the beginning, infinity at the end, a symmetry of birth and death. Some even imagine that the collapse could spark a new Big Bang, a cycle of universes, rising and falling, collapsing and rebirthing endlessly, a cosmic heartbeat, echoing across infinities of time. Another ending is quieter, but no less profound, the heat death. In this fate, expansion never reverses, it goes on forever. Galaxies drift apart, stars burn out, black holes slowly evaporate. Entropy, the measure of disorder, creeps toward its maximum. Over an infinite span, energy spreads so evenly that no differences remain, no gradients, no flows, no pockets of contrast, to power stars or stir life. The universe becomes a vast, silent ocean of uniformity, dark, cold, still, not a sudden end, but a slow fading, a long, infinite dusk. The timescales strain imagination. Billions of years for stars, trillions for galaxies, and then numbers so huge they lose their meaning. Even protons may decay. Even black holes, the most enduring of all, will eventually whisper away their energy through hawking radiation. What remains is stillness, uniformity, a universe where time itself loses its direction because nothing is left to change. Heat death is infinity, not as fire, but as waiting, an infinite future, where silence stretches without end. And then there is the most unsettling vision, the Big Rip. Here, dark energy does not stay constant. It grows. It strengthens. The expansion of the universe does not simply continue. It accelerates, faster and faster, until bonds cannot hold. Galaxies are torn apart. Stars pulled from their galaxies. Planets pulled from their stars. Even atoms themselves, ripped open, as space stretches without mercy. In this vision, the universe ends not in collapse, or in silence, but in tearing, a catastrophic unravelling of everything. Distances grow to infinity in a finite time. The fabric of space-time itself is stretched past endurance. Unlike heat death, which drifts toward eternity, the Big Rip has a schedule. It could come in tens of billions of years, or it might never happen at all. Its uncertainty only deepens its unease. It hangs like a possibility, a reminder that the cosmos may not simply fade, but could be torn apart. 3 endings. The Big Crunch. Infinity and density. Everything collapsing to a single point. The Heat Death. Infinity in time. A silence stretched endlessly into the future. The Big Rip. Infinity in expansion, where distances grow without bound until nothing holds together. Each possibility is infinite in its own way. Each is a mirror held up to the same cosmos, and whichever proves true, the end of the universe, like its beginning, forces us to face infinity, not as an abstract symbol, not as a mathematical curiosity, but as something woven directly into the fabric of existence itself. The cosmos does not end cleanly. It fades, sometimes in fire, sometimes in silence, sometimes in an endless stretch of stillness. The heat death whispers of infinity in time, a slow surrender to uniformity and quiet. The Big Rip presents infinity in expansion, where distances grow without limit, and the universe itself unravels strand by strand. The Big Crunch imagines infinity and density, a collapse back into a single point, a mirror echo of the beginning. Each possibility, no matter how different, is bound to infinity in one form or another, as though the cosmos itself cannot conclude without brushing against the endless. But these are not the only stories told. Some physicists imagine bouncing cosmologies, universes that never truly end, but expand and collapse in endless cycles, like a heartbeat, a cosmic inhale and exhale, repeating forever. Others picture strange futures, emerging even from the cold stillness of heat death. In the dark ocean of maximum entropy, quantum fluctuations may still stir. Rare events might appear. Boltzmann brains, fleeting sparks of thought, disembodied minds, wondering how they came to be. Or perhaps new universes might bubble into being, sprouting from the vacuum itself, each one a new beginning, born out of infinite time. Here, the end is not truly an end. It is a transition, a doorway, a bridge to something else. Infinity does not only stretch outward toward the vastness of space, it also turns inward, sinking into the very small. One of the oldest questions humanity has ever asked is simple yet dizzying. Can reality be divided forever? Take a stick, break it in half, break one of those halves again, and again, and again. Does this process go on without end? Or at some hidden depth, do we reach a smallest piece, a final, unbreakable grain of reality, the puzzle of the infinite decimal, the whisper of numbers that never stop, the riddle of whether the universe is built from endlessly smaller parts, or whether nature, at some point, draws a line and whispers, no further. The ancient Greeks wrestled with this mystery. Democritus imagined that all things were made of indivisible units. Atoms, he called them, from the word meaning uncuttable, tiny eternal building blocks, invisible, yet combined in endless ways to make the visible world. Others disagreed. They believed matter was smooth, continuous, infinitely divisible. Aristotle, for example, argued that you could always divide again, and again, and again, with no final bottom. Both visions were alluring. Atoms promised clarity. a neat solution to the strange paradoxes of infinity. Endless divisibility fit the flowing experience of life itself. After all, when you run your hand through water, you do not feel little grains. You feel a seamless stream. For centuries, the debate remained unresolved. A quiet question, echoing in philosophy, whispering in mathematics, lingering like a ghost in the background of science. Can you keep dividing forever? Or does nature, at some hidden threshold, place a final stone in the path, a smallest step beyond which there is no further road? For a long time it was only a dream, an argument traded across parchment and candlelight. But slowly, patiently, our instruments sharpened, our theories grew bold, and the ancient riddle of the smallest thing shifted its weight. It was no longer only philosophy, it was becoming physics. In the 17th century, a new tool appeared, a kind of sorcery written in symbols: calculus, born almost simultaneously in two different minds, Isaac Newton and Gottfried Wilhelm Leibniz. It was a language that leaned heavily on the idea of the infinitely small. Imagine taking steps so tiny, so delicate, that they shrink toward nothingness. They never quite vanish, yet they can be pushed closer and closer to zero, as though brushing the very edge of non-existence. With these ghostly steps, mathematicians could measure change, the slope of a curve, the area beneath a graph, the acceleration of a falling apple, the sweep of planets through their orbits. Suddenly, motion and growth, once messy and mysterious, could be described with dazzling precision. Without calculus, modern science, modern engineering, modern life itself would be unimaginable. But not everyone was convinced. To many, this use of infinitesimal steps felt suspicious, as though mathematicians were sneaking phantoms into their work. The philosopher Bishop Berkeley famously mocked them, calling these strange quantities the ghosts of departed quantities, neither truly zero nor truly finite, a slippery in-between. Over time, a firmer foundation was built. Mathematicians clarified the concept with the machinery of limits. Instead of treating infinite decimals as real physical things, they reframed them as a process, a quantity shrinking smaller and smaller, forever approaching a limit, but never needing to reach it. With this, calculus sidestepped the need to imagine an actual smallest piece of reality. It leaned instead on approximation, on the power of approaching closer and closer without end. And yet, outside of mathematics, the deeper question still lingered. Was nature itself continuous? Or was there, in the physical world, a smallest indivisible unit? The 19th century brought an answer that seemed to echo Democritus's dream. The atom was discovered. Matter, it turned out, was not smooth after all. It was granular dot built of tiny indivisible pieces, or so it seemed. Atoms were made of protons, neutrons, and electrons. But then those protons and neutrons revealed deeper secrets. They were built from even smaller things, quarks. Electrons, as far as we can tell, stand alone, with no further layers beneath them. For a moment it looked as though the quest for the bottom had finally reached bedrock. But quantum physics would not allow the picture to stay so simple. Particles began to behave like waves. They smeared across space, no longer points, but clouds of probability. The neat image of solid marbles was replaced with something fluid, stranger, less certain. Philosophically, singularities are unsettling. If infinity exists inside black holes, then nature itself contains regions where our logic collapses. If instead they mark the limits of our theories, then they are signposts, pointing toward deeper laws still to come. Either way, they matter. They may be hidden, but they are far from irrelevant. Stand at a safe distance, and imagine watching one. Stars curve around its edge, like streaks of light across glass. A clock falling toward the horizon seems to slow and then freeze, suspended in endless time. And yet, from its own point of view, the fall is swift and final. Black holes are terrifying, but they are also beautiful. They remind us that the universe is not built for comfort. It is built for wonder, and perhaps black holes are not even final. Some theories suggest they may slowly evaporate, whispering away their energy through a process called Hawking radiation. Given enough time, far longer than the age of the universe so far, they may fade completely, leaving only questions in their place. Infinity, in this view, would not be eternal. It would be a fleeting shadow, a passing stage in the evolution of the cosmos. In the end, black holes remain, our clearest glimpse of infinity made real. Cosmic riddles wrapped in darkness, balancing at the boundary between the known and the unknowable. And black holes are not alone in this dance. Infinities appear elsewhere too, in the strange, unpredictable world of quantum physics. Quantum theory is famous for its strangeness, but one of its lesser-known habits is an occasional tendency to spit out infinities, often at the most inconvenient times. The equations that govern the subatomic world are dazzlingly successful. They predict experiments with uncanny accuracy, and yet, under the surface, they sometimes deliver impossible answers. Infinite energy, infinite probability. Clearly, the universe is not overflowing with boundless infinities. If it were, your coffee cup would glow like a tiny sun. The vacuum of space would collapse under the weight of limitless energy. Instead, physicists treat these infinities as warnings, signals that the math has been stretched too far, that the theory needs gentle correction. One of the most notorious places this happens is in the calculations of particle interactions. In quantum field theory, particles are not little marbles. They are ripples in invisible fields. The photon is a ripple in the electromagnetic field. The electron is a ripple in the electron field. When two particles interact, the math describes them as exchanging virtual particles, fleeting messengers of force. But when you try to calculate these exchanges in detail, the sums spiral out of control. As you include higher and higher energies, the answers balloon toward infinity. For physicists of the early 20th century, this was a crisis. How could a theory filled with infinities ever describe reality? The solution, devised in the mid-20th century, was something called renormalization. It may sound like a suspicious trick, but it works brilliantly. The idea is this: the raw numbers that the equations produce are not the quantities we actually measure. Instead, we carefully redefine masses, charges, and energies. In doing so, the infinities are absorbed, and what remains are finite, beautifully accurate predictions. It is not that the infinities disappear. They are swept aside, folded into definitions, tamed by clever bookkeeping. At a singularity, the laws we know no longer apply. Infinity is not just an idea. It is written into the equations themselves. But what does it mean? Is there truly such a point of infinite density? Or is it a signal, a flare telling us our theories have reached their limit? Many physicists suspect the latter. General relativity is powerful, but not complete. It may need to be woven together with quantum mechanics before the picture comes clear. For now, singularities remain hidden, wrapped inside the dark silence of the event horizon. The horizon, the point of no return. Cross it and nothing comes back. Not light, not stars, not even the boldest astronaut. From the outside, the horizon appears as a dark sphere, an outline where light itself falls silent. Beyond it, all paths curve inward, toward the waiting singularity. Near a black hole, time itself slows. An object falling in appears to freeze in place, stretched thin, its light fading away. And yet, from its own perspective, the fall is swift and final. Infinity shows itself here too, not only as a singularity, but in the strange way time is perceived. An endless pause in one frame, a rushing plunge in another. Black holes, laboratories of the infinite, dark mirrors of the cosmos, reminding us that space and time still hold mysteries far beyond our reach. Some are small, born from the collapse of a single star. Others are giants, millions, even billions of times the mass of our sun, sitting quietly at the hearts of galaxies. These supermassive black holes rule their surroundings. They stir the orbits of stars. They bend rivers of gas. They launch great jets of energy that stretch for thousands of light years. It is astonishing to think that the very centers of galaxies are governed by objects whose defining feature is an infinity buried deep within. And yet, the singularity itself remains hidden. General relativity insists it must exist, but quantum theory whispers otherwise. Perhaps the singularity is not a true point of infinite density, but a region softened by quantum effects. Some ideas, like loop quantum gravity, suggest that space and time have a smallest possible scale, a kind of pixelation of reality. If so, infinities cannot form. The collapse would bounce, or resolve into something new. Others turn to string theory, where the smallest building blocks are not points, but vibrating strings. Here too, infinities are tamed by hidden structure. None of these possibilities are proven, but they reveal a deep truth. The singularity forces us to confront the unfinished business of physics. Even without peering inside, black holes reveal themselves in other ways. They warp the space around them. They draw in gas, spinning and spiraling toward the horizon. As it falls, it heats to blazing temperatures, shining in X-rays, sometimes brighter than entire galaxies. And black holes do not live in silence. They collide, they merge, and when they do, they ripple the very fabric of space-time. These ripples dot gravitational waves, wash across the cosmos, and we can now detect them here on Earth. Each one a whisper of infinity, echoing from a place where matter meets its end. The Big Bang, a hot, dense beginning, the first spark of a stage on which everything else would play out. Yet that stage may not be the only one. Beyond every horizon, beyond every bubble of the visible, there may lie others, not as empty extensions of our own, but as a patchwork of countless universes. Some may look like ours, lit with stars and galaxies. Others may be utterly alien, their forces arranged differently, their particles dancing to unfamiliar rules. The multiverse, it sounds like a dream, but it arises not from fantasy, rather from the mathematics of inflationary theory. And if there are infinitely many universes, then perhaps some contain versions of us, lives almost the same, but with small, delicate differences. In one, perhaps you sit with a cup of tea instead of water. In another, Perhaps Hubble never looked to the sky, and humanity still believes the cosmos is static. Infinity allows for every twist, every variation, every thread of possibility to play out. Somewhere, this is both thrilling and unsettling. Not all scientists embrace the multiverse. Some argue that without direct evidence, it drifts too far into speculation. Others counter that it may leave traces, subtle fingerprints in the cosmic microwave background, patterns hidden in the faint afterglow of creation. The debate continues, voices rising on both sides. What is certain is this: inflation, whether eternal or not, reshaped our understanding of beginnings, and the expansion, it has not slowed with age, it has quickened. Observations of distant supernovae revealed that galaxies are not just receding, they are receding faster and faster. Something unseen, now called dark energy, appears to be driving this acceleration. Its nature is unknown, but its effect is undeniable. The universe will keep stretching, carrying galaxies ever farther apart. One by one, they slip beyond our cosmic horizon, vanishing into silence. Our observable bubble shrinks, even as the whole grows larger. It is a picture that is both lonely and strangely inspiring. We live in a restless cosmos, forever unfurling, forever opening outward. The stars we see are but a fraction, and with every passing moment, more of them drift beyond reach. Infinity may never be something we can measure, but expansion whispers to us. The cosmos is larger than imagination itself. All of this vastness, began with the careful study of faint smudges of light through a telescope. Hubble-SIP's smudges became the key to unlocking an ever-expanding stage. From those small clues grew grand theories of inflation, of multiverses, of infinite horizons. The universe is not a still stage, but a living structure, a restless fabric, forever unfolding. Infinity may lie out there, just beyond every horizon. Perhaps our universe is one bubble among many, or perhaps it is the single endless stage on which all stories are told. We may never know, but the question itself carries a kind of quiet beauty. To live in an expanding universe is to know there is always more, an endless frontier, sliding gently into mystery. And then there are black holes, strangest of all objects, perfect meeting points between the ordinary and the infinite. They begin with something simple: gravity, the same force that holds you to the earth, the same force that keeps the moon circling in the sky. But when enough mass collapses, gravity grows extreme. A star, having burned through its fuel, falls into itself, and in its final collapse, it may become a black hole, an object so dense that not even light can escape. Einstein-SIP's equations describe this process with unsettling precision. The mathematics shows space itself curling inward, time itself bending. Push the equations far enough, and they whisper of singularity, a point of infinite density, a point where the fabric of space and time tears apart. This hints that the universe may indeed be infinite, or at least so vast that any curve is beyond our instruments to detect. Still, the door is not closed on other options. It could be finite, yet unimaginably large, like Earth's surface which has no edge, yet is not endless. Replace the two-dimensional surface with three-dimensional space, and you glimpse a cosmos that folds back on itself, quietly looping without walls. If you could travel straight through such a universe, you might someday return to where you began, but the journey would be so long, that not even a single ray of light has yet completed the trip, and expansion complicates the picture. Because it is not the galaxies themselves rushing away from us, it is space itself quietly stretching beneath them. So distant galaxies recede faster than light. This does not break relativity. It is the fabric of the cosmos unfolding, carrying its jewels farther and farther apart. It means there are regions we can never see, no matter how long we wait. They slip beyond our horizon, like ghostly ships drifting into the fog, never to return. Infinity may be hiding there, but we will never confirm it directly. We live in a finite bubble, surrounded by the unknown. There is also the possibility that space has a stranger shape. It may wrap around in unexpected ways, like a three-dimensional echo of a video game world, where leaving one side of the screen makes you appear on the other. In such a cosmos, light itself could circle around, arriving from behind us, painting ghostly copies of the same galaxy in different directions. Scientists have searched the sky for such repeating patterns, but so far nothing. If the universe does loop in this way, its loops lie far beyond our reach, and so we return to the possibility of infinity. If space is truly endless, then every possible arrangement of matter must occur somewhere. Somewhere out there, another planet like Earth. Another version of you, listening to these words. Not just one such twin, but infinitely many, scattered across the boundless sea of stars. This is not fantasy. It is a quiet implication of infinity, combined with the finite ways matter can arrange itself. We will never meet these distant doppelgangers, but the thought itself stretches the imagination into dizzying spaces. Infinity, though, carries its own challenges. An infinite universe would hold infinite stars, infinite galaxies, infinite energy. How do you speak of probability in such a realm? If there are infinitely many versions of every possibility, what does it mean to say one outcome is more likely than another? Physicists wrestle with this puzzle. Some whisper that infinity should be handled with caution, or perhaps avoided altogether, in physical theories. And yet a finite universe is not simple either. If the universe is like a sphere, then what lies outside it? The answer is nothing, because the space itself is the surface. To ask what lies beyond is like asking, what is north of the North Pole? The question dissolves as soon as you hold it. This is the beauty of a finite but unbounded cosmos. No edge to strike against, no wall to imprison us, yet no need for the vertigo of infinity. Whichever picture proves true, the cosmos leaves us humbled. Whether it is endless, or simply unimaginably vast, it lies forever beyond the reach of our travels. We will touch only our small bubble, but within that bubble are clues. The faint light of the early universe carries whispers of curvature. The clustering of galaxies hints at the hidden shape of space. We may never know with certainty whether infinity lives in the cosmos, but each observation circles closer, like a moth moving around a flame. Stand beneath the stars on a clear night, and the mind cannot help but stretch outward. Does the universe roll on forever, or is it a great loop, folding back upon itself? Perhaps we will never fully know, but the wondering is itself a kind of journey. Infinity in space is not only an answer we seek, it is an invitation to walk beyond the visible horizon, to dream outward, knowing that however far the imagination wanders, there will always be more waiting beyond. For centuries, many believed the universe was static. The stars hung in space like jewels upon velvet, unchanging, eternal. Then, in the 1920s, a man named Edwin Hubble pointed his telescope outward and saw something astonishing. The galaxies were not still. They were moving away from us. Not just a few, not just in one direction. Nearly all of them, in every direction. And the farther away they were, the faster they receded. The universe itself was expanding. Space was stretching. It meant the cosmos had not always been as it is now. Run the film backward, and everything draws closer, until, at last, all matter and all energy converge, not into a place within space, but into the very birth of space itself, and of time itself. Stars will one day burn out. Galaxies will drift apart. The cosmos will thin into silence and darkness. Physicists call this the heat death, a future where energy is evenly spread and nothing new can happen. It is an infinite future, but a quiet one, almost dreamless. Other theories suggest a more dramatic end. If dark energy behaves differently than we expect, expansion may accelerate until galaxies, stars, planets, even atoms themselves are torn apart. This big rip would be not an eternal future, but a sudden unravelling. Our own lives mirror these cosmic mysteries on a smaller scale. To each of us, time feels like a straight arrow moving quietly from birth to death. But in the sweep of history, it looks endless. Civilizations rise and fall like waves upon a shore, yet the ocean of time continues on. We each taste only a single drop, brief and fleeting, but cannot help wondering whether the river itself has a source or a mouth. And then there is the idea of recurrence. The philosopher Friedrich Nietzsche, inspired by the Greeks, asked us to imagine something strange, something dizzying. That every event in our lives will be repeated forever, exactly as it has happened before. Every joy, every sorrow, every small choice, looping endlessly through time. It was not meant as a scientific claim, but a challenge to the soul. Would you embrace your life if you knew it would recur infinitely? Infinity here becomes not a question of physics, but a mirror for perspective. Physics brings its own puzzles. If time is infinite, then even the most improbable events must eventually occur. Given endless time, every possible configuration of matter will one day appear. There might be another Earth, with another you living almost the same life. Except perhaps tonight you chose a different bedtime story. This stretches imagination to its limit, and yet it is a serious scientific puzzle, touching on probability, meaning, and identity in an endless timeline. And still, despite all these possibilities, time itself remains silent. We cannot step outside it to see whether it has an edge or a loop. Every clock ticks forward, every memory looks backward, and the rest remains hidden. Scientists build models. Philosophers weave arguments. Poets dream of eternity. But the truth may lie just beyond the horizon of what we can measure. What we can say is this: time, whether infinite or finite, gives shape to our experience. Without it, there would be no motion, no change, no life. The mystery of whether it stretches forever or began with a single spark does not diminish it. Instead, it deepens its wonder. Time is not simply numbers circling a clock face, but the stage on which the play of existence unfolds. Perhaps the most beautiful thing about infinity is that it can never be exhausted. Even if the universe had both a beginning and an end, our minds can still wander beyond them, imagining what lies before the first dawn or after the last night. Infinity and time, together, are both scientific hypotheses and canvases for imagination. They remind us that while each of our lives is brief, it unfolds within a mystery so vast, it cannot be contained by beginnings or endings. Whether time is an endless road or a circle folding back upon itself, it will always carry us forward, step by step, breath by breath. To ask whether it has boundaries is to stand at the very edge of comprehension, And in that silence where certainty fades, imagination finds room to dream. Look up at the night sky on a clear evening, and you are staring into one of humanity's oldest questions. Does it ever end? Do the stars scatter across an infinite canvas stretching forever outward? Or is the universe vast, but bounded, curving back upon itself? This riddle has teased astronomers, philosophers, and dreamers for centuries. The thought of infinite space is both thrilling and unsettling. It suggests a reality so immense that every direction leads outward without walls, without edges, without stopping. And yet, there is another possibility, just as strange, that the universe is finite, yet unbounded, like the surface of a sphere where you can walk forever and never reach an edge. The challenge begins with separating what we can see from what might exist. The observable universe is a bubble, centered on us, stretching some 46 billion light-years in every direction. It sounds impossibly large, and yet it is not the whole story. Light has a finite speed. The universe has a finite age, so we can only see as far as light has had time to travel. Beyond that horizon lies more universe, perhaps much more hidden from view. The observable universe is not the limit of existence. It is only the limit of visibility. A balcony, with a railing of light, overlooking an ocean we cannot yet cross. Cosmologists use geometry to frame the question. Einstein's theory of relativity tells us that space can curve depending on the matter and energy it holds. There are three possibilities: a universe of positive curvature, like a sphere; finite, but without edges. Travel far enough, and you might return to your starting point. A universe of negative curvature, like a saddle. Open, unbounded, stretching forever outward. Or a universe that is flat, neither sphere nor saddle, extending infinitely like an endless sheet of paper. Each possibility carries its own vision of reality, and deciding which is true is one of the great tasks of cosmology. Measurements of the faint afterglow of the Big Bang. The cosmic microwave background. Offer clues. Tiny ripples in that ancient light allow scientists to infer the shape of space itself, and so far, the evidence points toward flatness. In this vision, the universe ends not in collapse, or in silence, but in tearing, a catastrophic unraveling of everything. Distances grow to infinity, in a finite time. The fabric of space-time itself is stretched past endurance. Unlike heat death, which drifts toward eternity, the Big Rip has a schedule. It could come in tens of billions of years, or it might never happen at all. Its uncertainty only deepens its unease. It hangs like a possibility, a reminder that the cosmos may not simply fade, but could be torn apart. Three endings. The Big Crunch. Infinity in density. Everything collapsing to a single point. The Heat Death. Infinity in time. A silence stretched endlessly into the future. The Big Rip. Infinity in expansion, where distances grow without bound, until nothing holds together. Each possibility is infinite in its own way. Each is a mirror held up to the same cosmos, and whichever proves true, the end of the universe, like its beginning, forces us to face infinity, not as an abstraction, but as a reality, woven into the story of existence. When infinities rise up, they are not answers. They are invitations. They point to gaps in our knowledge, cracks in the scaffolding of our equations. They remind us, gently, that nature is subtle, careful, balanced, generous with structure and beauty, but never reckless. Energy is always conserved, always transformed, sometimes hidden in ways we do not yet understand. but never infinite, never unbound, never allowed to unravel the order of things. Infinity, then, is less about building impossible machines and more about listening to what physics is telling us. Each time it appears, it is as though the universe whispers, "Look deeper." It is a reminder that even our most powerful theories, elegant as they are still provisional, still incomplete, still maps, and not yet the territory. And there is comfort in this too, for the very laws that forbid infinite energy are the same laws that make stability possible, that allow stars to burn with steady light, galaxies to gather and spiral, and a fragile world like ours to rest in balance, for long enough that life may awaken and wonder. The universe had a beginning, or at least that is what most evidence suggests. The faint glow of the cosmic background radiation still lingers like an afterimage. The galaxies drifting apart, the expansion of space itself, all point backward to a hot, dense origin, nearly 14 billion years ago. If the cosmos had a beginning, it is natural, almost irresistible, to ask, will it also have an end? This question has haunted scientists, philosophers, and storytellers for centuries, and once again, infinity lurks in the answers. The possible endings of the universe are painted in shades of endless time, infinite density, and infinite expansion. One vision is the Big Crunch. Imagine gravity, the same quiet force pulling your feet to the floor, growing strong enough to halt the expansion of the universe and then reverse it. Galaxies would first slow, pause, and then begin to fall inward. The sky would grow brighter and stranger as galaxies crowd together, as stars collide, as everything begins to fold back in. Eventually, the entire universe would shrink into a state of unimaginable density and heat, a mirror image of its beginning. At the final moment, temperatures and densities would soar toward infinity, and there is comfort in this too, for the very laws that forbid infinite energy are the same laws that make stability possible, that allow stars to burn with steady light, galaxies to gather and spiral, and a fragile world like ours to rest in balance. For long enough that life may awaken and wonder. The universe had a beginning, or at least that is what most evidence suggests. The faint glow of the cosmic background radiation still lingers like an afterimage. The galaxies drifting apart, the expansion of space itself, all point backward to a hot, dense origin, nearly 14 billion years ago. If the cosmos had a beginning, it is natural, almost irresistible, to ask, will it also have an end? This question has haunted scientists, philosophers, and storytellers for centuries, and once again, infinity lurks in the answers. The possible endings of the universe are painted in shades of endless time, infinite density, and infinite expansion. One vision is the Big Crunch. Imagine gravity, the same quiet force pulling your feet to the floor, growing strong enough to halt the expansion of the universe, and then reverse it. Galaxies would first slow, pause, and then begin to fall inward. The sky would grow brighter and stranger as galaxies crowd together, as stars collide, as everything begins to fold back in. Eventually, the entire universe would shrink into a state of unimaginable density and heat, a mirror image of its beginning. At the final moment, temperatures and densities would soar toward infinity. Space itself would collapse. Time itself would buckle. The Big Crunch is the cosmos, folding back into itself, a grand return to a singular point, though current evidence, the accelerating expansion driven by dark energy, makes this fate seem unlikely. The Big Crunch still holds a certain poetry, infinity at the beginning, infinity at the end, a symmetry of birth and death. Some even imagine that the collapse could spark a new Big Bang, a cycle of universes, rising and falling, collapsing and rebirthing endlessly, a cosmic heartbeat, echoing across infinities of time. Another ending is quieter, but no less profound, the heat death. In this fate, expansion never reverses, it goes on forever. Galaxies drift apart, stars burn out, black holes slowly evaporate. Entropy, the measure of disorder, creeps toward its maximum. Over an infinite span, energy spreads so evenly that no differences remain, no gradients, no flows, no pockets of contrast to power stars or stir life. The universe becomes a vast, silent ocean of uniformity, dark, cold, still, not a sudden end, but a slow fading, a long infinite dusk. The timescales strain imagination, billions of years for stars, trillions for galaxies, and then numbers so huge they lose their meaning. Even protons may decay, even black holes, the most enduring of all, will eventually whisper away their energy. Through Hawking radiation, what remains is stillness, uniformity, a universe where time itself loses its direction because nothing is left to change. Heat death is infinity, not as fire, but as waiting, an infinite future, where silence stretches without end. And then there is the most unsettling vision, the Big Rip. Here, dark energy does not stay constant. It grows. It strengthens. The expansion of the universe does not simply continue. It accelerates, faster and faster, until bonds cannot hold. Galaxies are torn apart. Stars pulled from their galaxies, planets pulled from their stars, even atoms themselves, ripped open, as space stretches without mercy. It sounds delightful, too delightful. Because such a universe would be unstable, chaotic, unlivable. Any tiny fluctuation could unleash infinite power. Any spark could roar into a boundless storm. Stars would not endure. Planets could not hold together. Life could not arise in the flood. The impossibility of infinite energy is not a cruel restriction. It is a safeguard. It is the rule that makes stability, structure, and life itself possible. There are, however, ingenious ways in which physics can mimic eternity. Superconductors, for instance, can carry currents without resistance. Once set into motion, an electrical current can circle for years without losing its strength. It looks like perpetual motion, but it is not. The system still demands careful conditions. Fragile environments cooled near absolute zero, and crucially, no new energy is created. The current is only preserved, not conjured. Quantum systems, too, can linger in strange, long-lived states, metastable, delicate. They look eternal from afar, but they too obey the laws. No loophole, no free energy, only clever tricks that let the rules play out in beautiful, unusual ways. Sometimes, the dream of infinite energy is reborn in cosmology, dark energy. The mysterious pressure driving the expansion of the universe is often whispered about as a hidden reservoir, an endless ocean of power, the ultimate fuel. But this too is illusion. Dark energy cannot be bottled or burned. It is not something we can tap. It is a property of space itself, woven evenly through the cosmos. Even if it carries energy, it does not violate the conservation laws. It cannot be bent to our purposes. Infinity, once again, is kept in check. In the end, infinite energy is less like a treasure chest and more like a mirage. Each time it appears in physics, it signals that we have pushed our equations past their domain. It is not the universe that is infinite. It is our models that are incomplete. Perpetual motion remains a dream, not because engineers lack imagination, but because the universe is ruled by laws that no gear or magnet can overthrow. Infinity breaks physics, not because the cosmos dislikes large numbers, but because real energy must always balance, must always flow, must always transform. When infinities rise up, they are not answers. They are invitations. They point to gaps in our knowledge, cracks in the scaffolding of our equations. They remind us, gently, that nature is subtle, careful, balanced, generous with structure and beauty, but never reckless. Energy is always conserved, always transformed, sometimes hidden in ways we do not yet understand, but never infinite, never unbound, never allowed to unravel the order of things. Infinity, then, is less about building impossible machines, and more about listening to what physics is telling us. Each time it appears, it is as though the universe whispers, "Look deeper." It is a reminder that even our most powerful theories, elegant as they are still provisional, still incomplete, still maps, and not yet the territory. Quantum theory, with its strange fluctuations and restless zero-point energy, sometimes tempts us with loopholes. After all, the vacuum itself is not empty. Particles flicker in and out. Energy jitters in the background. Could this be harvested, tapped like an infinite fuel? The answer, quietly but firmly, is no. These fluctuations cannot be captured like sunlight. They cannot be scooped up and poured into a bottle. To gather them would always demand more energy than they could ever return. They are not a free lunch. They are not an endless battery waiting to be tapped. They are a kind of background murmur, restless noise, a shimmer in the void, the universe humming softly to itself. Even here, in the deepest emptiness we can imagine, the cosmos remains stingy, careful, meticulous. It doles out its energy according to rules, rules that are unwavering, rules that are old and deep, rules that never let infinity take hold in practice. And yet, infinities appear again and again in our calculations. They rise up in equations like weeds through stone. In quantum field theory, when you add up all the possible particle energies, the sum climbs without bound. Left untreated, the numbers explode, predicting infinite densities, infinite fields, infinite energies that cannot exist. Renormalization was developed to tame this, a method of redefining the quantities, so that the infinities cancel one another, and what remains is finite, reasonable, measurable. It works. In fact, it works astonishingly well, but its very success is also a reminder of how fragile our models really are. Infinity whispers to us that equations are not reality. They are only maps, maps that sometimes stretch too far from the terrain they were drawn to describe. Classical physics, too, was no stranger to infinity-seps tricks. Consider the problem of the electron. Early on, physicists treated it as a tiny point, a single speck of charge, compressed into nothingness. But the electric field of such a point grows stronger and stronger. The closer you approach, at zero distance, the strength becomes infinite. That would mean the electron carries infinite self-energy, a bubbling, boundless reservoir, locked inside a particle smaller than imagination. Clearly, this cannot be so. Electrons do not tear the universe apart. They do not sit there radiating infinities. The infinity here is not real. It is the echo of a model pushed too far. Quantum mechanics softened the picture. The electron became not a point, but a probability cloud, a haze of possible locations. The harsh spike of infinity blurred into something gentler. Even so, questions about self-energy remain. They are still puzzles, still playgrounds, for physicists searching for deeper truths. Infinity returns in perhaps its most dramatic form. When we turn our eyes to the beginning, the early universe, the Big Bang. According to general relativity, the equations of gravity drive us back to a singularity, a point of infinite density, infinite temperature, infinite curvature of space and time. But these infinities are not physical things. They are warning lights. They are alarms ringing loudly, telling us our theories cannot yet reach into that first instant. They shout to us that new physics is required, perhaps quantum gravity, a deeper framework that blends the graininess of the quantum with the sweep of relativity. Infinities here are not answers. They are boundaries. They are signposts marking the end of what we know. It is worth pausing to ask what the world would truly be like if infinite energy were possible. Imagine a kettle that boiled forever without a plug, a car that ran endlessly, its tank never emptying, refilling itself out of nothing. Our moment is temporary, a flicker carved against a tide that will one day flatten everything. And yet, within this fleeting window, complexity blooms, awareness awakens, meaning is found. Infinity ensures entropy will one day win, but it also ensures that improbable wonders, including our own existence, have their chance to appear. The arrow of time keeps pointing forward, drawing us with it. And as it does, entropy writes the universe-sept story across infinite pages. Each moment of order is precious, unrepeatable, a spark glowing briefly against the endless drift toward equilibrium. Perhaps the deepest beauty of entropy is that it makes every instant unique, every moment irreplaceable, every life unrepeatable, and therefore all the more meaningful, even against the vast backdrop of infinity. But infinity is restless. It has a curious way of sneaking into equations and causing chaos. Mathematicians may treat it as a useful abstraction, a symbol that stretches beyond numbers. But in physics, infinity often spells disaster. When a formula spits out infinite energy or infinite density, it is almost never describing reality. It is warning us that the theory has been pushed beyond its limits. Nature, as far as we can tell, does not trade in infinities. It keeps its ledgers finite, balanced. If it did instead, we would be living in a very different universe. A universe where light bulbs blaze like stars, where perpetual motion hums in every kitchen, where energy flows without end. But that is not the world we find. To see why infinity is so disruptive, consider the conservation of energy. This principle, one of the bedrocks of physics, says energy cannot be created or destroyed. It can only be transformed. The total energy of a closed system remains constant. Drop a ball, and its potential energy turns into kinetic energy. Rub your hands together, and motion warms into heat. The ledger always balances, but introduce infinity, and the ledger collapses. An infinite amount of energy has no counterweight, no balance point, no way to fit into a finite account. It is like trying to pour the ocean into a teacup. The mathematics floods over the rim, the meaning spills away. Perpetual motion is perhaps the most persistent dream, born from the allure of infinite energy. For centuries, inventors have tried to sketch machines that would run forever without fuel. Wheels weighted to spin endlessly, magnets arranged in loops without end, contraptions designed to feed on their own motion, like snakes devouring their tails. All of them were clever. All of them failed. Not because of lack of ingenuity, but because of the laws of thermodynamics. The first law, conservation of energy, forbids creating energy from nothing. The second law, the rise of entropy, ensures that some energy is always lost as heat, always slipping away, always dissipating. Perfect efficiency is impossible. A perpetual motion machine is not just impractical. It is forbidden by the very framework of physics. If so, how can we trust our own memories, our science, our sense of time? Are we true observers in a genuine cosmos, or only temporary fluctuations, passing sparks in the endless dark? Most physicists recoil from this conclusion. They suspect it reveals something incomplete in our understanding of entropy, or time, or the cosmos itself. Another strange twist emerges from infinity: recurrence. In a finite system, if time is infinite, states will eventually repeat. Imagine shuffling a deck of cards forever. Eventually, every possible order will arise, including the one you began with. By extension, if the universe has a finite number of states, and time is infinite, it could someday return to conditions nearly identical to today. The arrow of time would still point forward, but the scenery would loop over and over. Eternity as repetition. Entropy even casts its shadow backward, into the very beginning. The Big Bang was not only hot and dense, it was extraordinarily low in entropy compared to today. That may sound strange. How could the beginning of everything be less random than the present? One idea is that gravity changes the rules, making early uniformity a kind of hidden order. Another possibility, our observable universe, is just one small pocket within a much larger system, and we happen to arise in a rare bubble of low entropy. Infinity leaves room for such unlikely beginnings. Despite its bleakness, there is a quiet beauty in entropy. It is the law that gives time a story. It is the reason memory exists, the reason history unfolds, the reason we live in a universe that moves from past to future. Without entropy, time would lose its direction. The cosmos would lose its tail. Entropy is not just the shadow of decay. It is the very engine of becoming. It is the reason stars ignite and burn, the reason galaxies spiral and grow, the reason life takes root in hidden corners of the cosmos. Entropy means there is a story at all, a story written in fire and dust, in rivers that carve valleys, in forests that rise and fall, in civilizations that remember, and in memories that fade. Entropy means the world does not sit still. It shines, it flows, it changes, and out of this constant shift, complexity climbs upward, life unfolding from simplicity, awareness awakening from matter. Infinity may stretch entropy toward bleakness, toward the far-off silence of the heat death. But here, in the finite chapters we inhabit, it is the driver of everything lively and bright. Entropy Sip's arrow also shows how deeply infinity and probability are braided together. On ordinary time scales, entropy ensures broken cups stay broken. Fires burn only one way. Smoke drifts outward but never inward. But stretched across infinite horizons of time, the same law allows even the most absurd fluctuations, galaxies spontaneously reassembling, particles reshuffling themselves into order, Boltzmann brains flickering alive, pondering their own unlikely existence, before dissolving back into the dark. The ordinary and the bizarre spring from the same rule, stretched across different scales of time. So the second law, often simplified as things fall apart, is not merely about decay, it is also about possibility, about the universe Sep's relentless drive to explore every configuration it can. In the short term, this gives rise to stars, to planets, to life, to thought. In the long term, it drifts toward equilibrium, and over infinity, it opens doors so strange they border on philosophy. To contemplate entropy and infinite time is to glimpse both the fragility and the resilience of order. Entropy is the mathematics of possibility. It is the arithmetic of disorder, and one law above all governs it, the second law of thermodynamics. In a closed system, entropy never decreases. It may pause for a moment, it may stay steady for a while, but given enough time, it always increases. This law, more than almost any other in physics, gives time its arrow. The arrow of time points forward, because entropy rises. It is why you know instantly that a glass falling and shattering on the floor is running in the correct direction. You never see the shards leap up, reforming into a perfect vessel. The laws of physics do not forbid such a miracle. At the microscopic level, every motion could be reversed. But the odds are so staggeringly, so impossibly small, that for all practical purposes, they are zero. Order slides into disorder, never the reverse, and the universe keeps flowing forward. But what happens when you stretch this simple rule across infinite time? If entropy must always increase, does it climb forever? Does it have a ceiling? The answer, sobering and strange, is yes. Entropy has a maximum, and when it is reached, the universe enters a state we call the heat death. Overspans so long they erase the imagination. Stars will burn out. Galaxies will fade. Energy will thin itself across the cosmos until it is evenly spread, without gradients, without contrast, without fuel. Entropy will be at its peak, and when it is, nothing interesting remains. No new stars will ignite. No planets will form. No flows of heat or rivers of light to carve new patterns, just silence. A vast evenness, a flat ocean of stillness, not because energy is gone, but because it has been diluted, smoothed out, so evenly distributed that nothing more can be done with it. The time scales are staggering. Our sun will shine for billions of years yet, but black holes will outlast it by far more. Even they will not live forever. Through the slow process of Hawking radiation, the largest of them will eventually evaporate into faint whispers of light. But this will take 10 sane descent years or more. Numbers so large, they make the entire age of the universe so far seem like the blink of an eye. After that, darkness. Space expanding ever further. Particles drifting alone. entropy creeping toward its final ceiling, a future without end, a desert of stillness, infinity as silence, and yet infinity never plays fair. Given infinite time, even events that are almost impossible become inevitable. The unlikely eventually occurs. The absurd becomes real. This is where the strange idea of the Boltzmann brain emerges. In a universe ruled by maximum entropy, where order is almost gone, random fluctuations still stir the emptiness. Particles, drifting endlessly, can by sheer chance assemble into temporary pockets of order. Given enough time, they might even assemble into something complex, something as astonishing as a brain complete with memories, thoughts, a sense of self, a mind that believes it has lived a life, even though it has not. For a fleeting instant, it thinks, and then it dissolves, slipping back into the chaos. Absurd, yes, but mathematically, not impossible. This leads to a disturbing riddle. If the universe lasts forever, and Boltzmann brains emerge endlessly, are they more common than beings like us? Beings who arise through stars, and planets, and evolution. Infinite divisibility seem to resurface. A wave spreads continuously, but energy comes only in discrete packets. Quanta, tiny parcels of the unseen. Reality was neither entirely smooth, nor entirely grainy. It was something in between, something the human mind still struggles to picture. And then came the Planck scale, the final cliff perhaps, beyond which even our mathematics falters. The Planck lengths, about Surfel's Hall-the-Mice meters, a number so small that the very size of a proton is a vast continent in comparison. The Planck time, about Surfard Hartefard seconds, a slice of duration so brief that even a billionth of a second is an eternity beside it. At scales this small, our theories, quantum mechanics, relativity, fall apart. The Planck scale is often described as a threshold, a place where space-time itself may no longer be smooth, but granular, pixelated, like an image zoomed in until the screen reveals its squares. Does reality end here? Does the universe finally whisper, no smaller, no further? Some theories say yes. Loop quantum gravity imagines space, woven from tiny finite loops, knotted together like a fabric of threads. String theory envisions, not points, but vibrating strings, their size hovering around the Planck length, smoothing away infinities with their hidden music. In both pictures, the endless divisibility of space and time is cut short. Infinity, once feared, is tamed by structure, but others remain cautious. Perhaps the Planck scale does not mark the end, but only a warning sign, a place where our equations, like maps too roughly drawn, cease to guide us. Perhaps with a new framework, divisibility might continue even deeper still, and so the question remains open. Is the universe ultimately discrete, or continuous without end? The implications are profound either way. If space and time are granular, then infinity is exiled from the very fabric of the cosmos. No infinitely small distances, no infinitely brief moments, only the smallest units of existence. But if reality is continuous, then infinity lives inside every crack. It hides at the bottom of every division, waiting forever at the end of the line. And in practice, physicists live in both worlds. Calculus, with its infinite decimals, guides us with astonishing power. From the orbits of planets, to the flow of rivers, to the flutter of air over wings. Quantum mechanics, with its discreteness, holds infinities at bay, turning chaos into probability, the structure into law. It is a balancing act, a dance between the infinite and the finite, between smooth waves and discrete quanta. For everyday life, these debates may seem distant, yet there is something strangely comforting about them. The fact that such a simple question, "Can I keep cutting this in half forever?" still occupies the brightest minds alive today, reminds us of how deep infinity runs. Whether the universe is ultimately pixelated or endlessly smooth, the infinite decimal has already reshaped the world. It has become one of the most powerful ideas in human thought. So when you picture the universe, try to imagine both extremes. In one vision, reality bottoms out into indivisible grains, the atoms of space and time themselves, tiny bricks in a cosmic wall, stacked together to build all that we know. In the other, every line can be split again, every moment subdivided forever, a descent with no bottom, infinity hiding quietly in the cracks. Both possibilities are astonishing, both are unsettling, and both remind us that even in the smallest things, infinity waits, silent and patient. From here, let us drift into another corner of infinity's domain, entropy. The word drifts easily into conversations, a shorthand for disorder. But in physics, it carries a far sharper, far more precise meaning. Entropy is the measure of how many different ways a system can be arranged, while still looking the same from far away. A neat, ordered stack of playing cards has very low entropy, because only a few arrangements preserve the perfect order. Shuffle the cards into chaos, and suddenly the entropy rises. Now there are countless possible configurations, all equally messy, and yet Cantor proved that even fractions are countable. With a clever diagonal method, he showed that you could in fact list them all, one by one, without missing a single one. Then came the leap. What about the real numbers? Not just fractions, but the unruly decimals that stretch on forever, like the square root of 2 or pi. Here, Cantor discovered something extraordinary. No matter how you try to arrange them, the real numbers cannot be listed. Some will always slip through the net. This meant that the infinity of real numbers was strictly larger than the infinity of whole numbers. Infinity itself had layers. The infinity of the counting numbers, the infinity of fractions, and above them all, the vast infinity of the continuum. Cantor called these different sizes cardinalities, and the infinity of the real numbers he named the continuum. It was not just mathematics. It was philosophy, reshaped by numbers. His work was controversial, ridiculed by some, resisted by others, but over time it became one of the cornerstones of modern mathematics. Today, much of set theory. The very foundation of mathematics. Rests quietly on Cantor's bold step into the infinite. To taste just how strange infinity can be, imagine checking into Hilbert's Hotel. This thought experiment, dreamed up by the mathematician David Hilbert, shows the peculiar hospitality of the infinite. Picture a hotel with infinitely many rooms, numbered 1, 2, 3, and so on. Every single room is full, and yet a new guest arrives. No problem. The guest in room 1 moves to room 2. The guest in room 2 moves to room 3. And so on, endlessly down the line. Room 1 is free, and the newcomer settles in. But the strangeness deepens. Suppose an entire bus. Filled with infinitely many new guests. Arrives. Still no problem. Each current guest moves from room n to room 2n, doubling their room number. Now all the odd-numbered rooms are vacant, infinitely many of them, ready for the infinite busload. In fact, no matter how many infinite crowds arrive, Hilbert's hotel always finds a way to welcome them. Infinity seems endlessly accommodating, a host that never turns anyone away. But try checking out of the hotel, and the paradox grows stranger still. If everyone leaves except the guest in the first room, the hotel still contains infinitely many occupants. If the guests in every second room leave, infinity remains. Subtracting infinity from infinity is not like subtracting apples from a basket. The result depends entirely on how you choose to subtract. Infinity is generous, but also mischievous. It bends rules we thought unbreakable. With finite collections, logic is straightforward. 10 apples, remove 5, and you are left with 5. But with infinity, halves can equal wholes. Subtraction may leave you right back where you started. What feels like nonsense at first is simply the peculiar landscape of endless quantity. For mathematicians, these insights are not just games, but essential tools. Calculus, for instance, rests on infinity's quiet shoulders. To calculate the slope of a curve, you imagine shrinking a step smaller and smaller, approaching an infinite limit. The result is not infinity itself, but the shadow of infinity at work. Similarly, infinite series. Endless sums. Sometimes fold themselves down into finite answers. 1/2 plus 1/4 plus 1/8, and so on forever, approaches 1. Infinity hides inside these processes, yet delivers calm, finite results. There is something humbling in all this. Infinity in mathematics is both playful and profound. It reminds us that our simplest tool. Numbers. Contains depths we can never exhaust. Start with simple counting, and soon you find yourself in a hotel that never fills. Climb further, and you discover a ladder of infinities, each one larger than the last. Step by step, rung by rung, into a sky that has no top, into the unknown, into paradoxes that defy common sense. The ancients may have wondered whether infinity could truly exist. But by stepping into the world of numbers, humanity discovered that infinity was not just an idea hovering above us. It was built into the logic of counting itself. Every time a child asks what comes after the biggest number, they are already brushing against the endless. Numbers whisper to us that infinity is not distant, not only at the edge of the cosmos. It is right here, embedded in the most ordinary act of saying, one more. And numbers are not alone. Time too carries the flavour of infinity. Time is the quiet river that carries every life forward. It slips past without effort, relentless and smooth. It leaves us with memories of what has gone and expectations of what may come. And so, when people began to wonder about infinity, their thoughts often drifted naturally toward time. Could time itself stretch endlessly backward into the past? Or did it have a first moment? Will it continue forever into the future? Or is there a hidden wall ahead, a final stop? These questions strike at the heart of what infinity means, not only for physics, but for our very sense of existence. Many ancient traditions pictured time as a cycle rather than a line. The Babylonians, the Egyptians, the Indians, the Greeks. Each saw the eternal return of the seasons, the rising and setting of the sun, the birth and death of generations. Time appeared to them as a great wheel, turning endlessly. In Indian cosmology, vast spans called yugas measured ages of creation and destruction, rolling one into another without end. The Greeks spoke of eternal recurrence. The haunting idea that the universe endlessly repeats itself. In such a vision, the future is not new, but familiar, a repetition of what has already been, over and over, without end. Philosophers debated the possibility of infinite regress in time. If every event must have a cause, and every cause has another before it, Where does it all begin? Does the chain of causes stretch backward forever? Some argued yes, that there could be no first cause, only an endless sequence. Others insisted that an infinite regress was impossible, that time must have had a definite starting point. Aristotle leaned toward the eternal view, reasoning that something could not arise from absolute nothing. Centuries later, Christian theologians took the opposite stance, affirming a moment of creation when God brought forth both time and the universe together. Modern science eventually found its own voice in this debate. With the rise of cosmology in the 20th century, evidence began pointing toward a beginning, the Big Bang. About 13.8 billion years ago, the universe expanded from a state of unimaginable heat and density. It was not an explosion within space, but the birth of space and time itself. In this picture, time had a starting point. To ask what happened before may not even make sense, because time itself was born in that moment. And yet, the debate is not closed. Some cosmologists imagine that the Big Bang was not the first beginning, but merely a transition. Perhaps the universe collapses and rebounds endlessly in cosmic cycles, a great bouncing rhythm without a first beat. Others picture eternal inflation, a vast space where bubble universes like our own are constantly budding and blooming. If so, our cosmos is but one story in an endless library. The future, too, is a stage for infinity's riddles. If the universe continues to expand without bound, then time stretches forward endlessly. But what kind of eternity awaits? The Babylonians and Egyptians too brushed against infinity in their cosmologies. The endless dome of stars overhead suggested a space without limit, while the cycles of the Nile, or the steady return of the seasons, gave rhythm to a sense of eternal recurrence. In these ancient worlds, infinity was not an abstract symbol on a chalkboard, it was a lived experience. The endless flood, the eternal night sky, the perpetual return of day following night. It is striking, isn't it? How often different cultures return to the same quiet question. Does the universe have a boundary? To imagine a wall at the edge of the cosmos raises an immediate puzzle. What lies beyond it? If there is something beyond, then the universe is not truly bounded. And if there is nothing, how can nothingness itself have an edge? The human mind is unsettled by the idea of an end, but equally unsettled by the thought of no end at all. Infinity always sits at this uneasy border, refusing to let us rest too easily. Even in mathematics, the ancients sensed infinity's peculiarities. The Greeks, in particular, distinguished between potential infinity and actual infinity. Potential infinity was the idea that you can always add one more, always divide a distance again, without ever reaching the final stop. Actual infinity, by contrast, was the bold claim that infinity could exist as a completed whole, present all at once. Aristotle rejected this. To him, infinity could never be an actual state. It could only be a process, a journey without a destination. He believed infinity was something forever unfolding, never a finished picture. And this distinction still echoes in modern thought. When you count numbers, you never arrive at infinity. You simply move endlessly forward, each step revealing only the potential for another. Infinity is not a destination at the end of the road. Infinity is the road itself, stretching without limit. For the ancients, this endlessness was both a comfort and a torment. Religious traditions, too, embraced infinity often as a way of describing the divine. The gods were eternal, boundless, limitless. To call a deity infinite was to say beyond decay, beyond time, beyond measure. Infinity became a mark of the sacred, the perfect counterpoint to the fragile, finite nature of human life. What unites all of these perspectives? Greek, Indian, Taoist, Egyptian, Babylonian, is the same fascination with the endless. Whether through paradoxes of motion, cosmic cycles of time, eternal principles of nature, or mathematical debates, early thinkers could not resist infinity's strange allure. They pressed against the edges of human thought, only to discover that the boundaries themselves dissolved into the horizon. It is almost amusing how long ago these puzzles were first posed, and yet, even now they still hold their power. The tortoise still teases Achilles, the halved distances still wait for the walker, and the great mountain of the Kalpa still endures its silken brushing. The ancients may not have had modern physics or the language of set theory, but they were right to see infinity as a place where reason both falters and expands. In their own way, they handed us the first maps of the endless, maps not with destinations, but with invitations. Invitations to wander gently into the unknown. Because, in every culture that dreamed of infinity, the idea was not just a puzzle to solve, but a horizon to approach, forever receding, forever calling. Numbers too carry infinity quietly inside them. You only have to begin counting to see it appear. 1, 2, 3, 4, 5, and there is no stopping point. However far you go, another number is always waiting patiently beyond. Children discover this truth early, when they ask that impossible question, what comes after the biggest number? And the only honest answer is, there is no biggest number. Numbers are like stepping stones across a river that has no opposite bank. You can keep moving forward endlessly, with infinity always just out of reach. This is what we call potential infinity. It means there is no final stop, no crown to place at the end of the number line. Infinity is never a single point you can touch, Dotty. It is the process itself that is endless. Each step forward only creates the possibility for another. It feels natural, almost friendly, because we live with it so easily in our counting, our adding, our imagining of larger and larger totals. But the moment you scratch the surface, even here, strangeness begins to appear. Take the even numbers, for instance. At first, it seems obvious that the set of all whole numbers must be larger than the set of even numbers. After all, the evens are only half the list. But infinity plays by its own rules. For every whole number, you compare an even number. 1 with 2, 2 with 4, 3 with 6, and so on without end. This one-to-one matching shows that the set of even numbers is not smaller at all. In the infinite sense, it is exactly the same size as the set of all numbers. And the same is true of the odd numbers, the square numbers, even the primes. All of them stretch on forever. All of them can be paired neatly back to the original line. Infinity does not shrink just because you take half, or remove some of its parts. This strange elasticity puzzled mathematicians for centuries, until, in the 19th century, a German thinker named Georg Cantor decided to face infinity head-on. Cantor did not shy away, as so many before him had done. Instead, he studied the infinite directly, and in doing so revealed something astonishing. Not all infinities are created equal. To most people, infinity is simply endlessness. One vast, indistinguishable ocean. But Cantor showed that there are different sizes of infinity, stacked one above the other like a ladder without end. His discovery was so bold that many of his contemporaries resisted it fiercely. Cantor's first insight was to compare different sets of numbers. Whole numbers. 1, 2, 3, and so on, form what is called a countable infinity. You can imagine lining them up neatly, each one taking its place in the sequence. But what about fractions? Numbers like 1/2, 2/3, 27 over 99. At first glance, they seem far more numerous, since between any two whole numbers you can squeeze infinitely many fractions. Good evening, and welcome back to the Sleepy Professor. Tonight's journey is a gentle one. You are invited to let the world slow down around you, as if the ticking of clocks were softening and each moment were stretching just a little longer. This video is meant to be your companion as you unwind. Perhaps you are already nestled beneath warm blankets, or maybe you're simply letting your thoughts drift, like clouds loosening themselves across a quiet sky. Our theme this evening is infinity, that elusive, slippery idea that refuses to be fully held by mathematics, philosophy, or physics alike. But before we begin to wander into the endless, I'd love to know where in the world you are listening from. It always fascinates me to imagine these words traveling quietly across time zones and landscapes, reaching you wherever you are. If this video helps you to relax, or stirs your curiosity even just a little, a like and a subscribe would be a kind way of supporting the channel. And to those who have already joined the Sleepy Professor, thank you for being part of this little constellation of listeners. Each of you is a star glowing softly in this growing night sky we share together. Sometimes I worry that these stories might become too interesting, and that instead of lulling you to sleep, they might keep your mind awake. But then again, if you do stay up a little longer, at least you'll be drifting through the wonders of the universe as you slowly, gently begin to let go. And if your curiosity stretches not only to the stars above, but also to the landscapes of our own Earth, you might enjoy visiting my new channel, The Sleepy Geographer. There's a link waiting for you in the description, should you feel like wandering that way on another evening. For now, let us sail quietly into tonight's subject. Infinity. What does it mean when something has no end? Infinity is a word that feels simple on the tongue, but the moment you look at it closely, it begins to shift, to shimmer, to dissolve into something far stranger. From the endless steps of a paradox, to the possibility of a universe that stretches forever, infinity rests at the border between imagination and science. It has guided discoveries, yet also confused the very minds that sought to contain it. For as long as humans have gazed at the night sky, they have wondered whether the stars continue on without limit. Philosophers puzzled over the infinite centuries ago, trying to reconcile it with motion, with space, with the flow of time itself. Mathematicians later learned how to write infinity into the language of numbers, though it never came quietly. With each answer it offered, it seemed to hide a new puzzle behind the curtain. Even physicists today still wrestle with infinity, finding that their equations sometimes tumble off the edge into endlessness, while reality itself refuses to follow. Infinity touches every corner of thought. It lingers in the structure of space, in the ticking of time, in the restless energy of particles, even in the age-old question of how many worlds might exist, scattered through the vastness. It is a concept that cannot be contained. It is as much a mystery as it is a tool. This is why it has always been both feared and cherished. Without infinity, our equations might be tidier, smaller, but with it, our universe becomes immeasurably larger. Tonight, we will wander gently through infinity's many faces, from the paradoxes of the ancients, to the abstractions of mathematics, to the boundless horizons of modern physics, from the infinitely small to the endlessly vast. Along the way, there will be puzzles that delight, curiosities that confuse, and ideas so wide, so calming, that they feel like a lullaby sung by the universe itself. Infinity is not something you can hold in your hand, not even something you can picture clearly in your mind. And yet, it has a way of shaping how you think about everything. So tonight, let it unfold slowly, like a horizon receding into a quiet sky. Because once you begin to ask what infinity means, you discover you are stepping onto a path that may have no end. The ancients understood this too. Long before telescopes, or chalkboards filled with symbols, human beings imagined the endless. They felt its presence in the rhythms of the seasons, in the repeating cycles of day and night, in the steady, ceaseless beating of the heart. One of the first to bring infinity to the center of thought was Zeno of Elea, a philosopher from ancient Greece. Zeno didn't offer answers so much as riddles. His paradoxes were like little traps for the mind, designed to show how infinity lurks inside even the simplest actions. In one famous example, Zeno argued that to walk across a room, you must first walk halfway, then half of the remaining distance, and then half again and again and again, endlessly. By this logic, you would never actually arrive, and yet, of course, we do. It's a puzzle that sits like a pebble in the mind, at once frustrating and strangely soothing, because it reminds us that even something as ordinary as taking a single step contains echoes of the infinite. Zeno's stories may keep us awake with their curious twists, yet they also invite us to rest in wonder. The infinite is not only out there, among the stars, but hidden quietly in each motion, each breath, each moment that slips silently into the next. And as we drift further, we find that many cultures across many centuries have engaged with this same notion of endlessness. In Taoist thought, the Tao was often seen as eternal, boundless, a principle that underlies all things without beginning or end. The Tao Te Ching, attributed to Laozi, speaks of the Tao as something that cannot be fully named or captured, precisely because it is limitless. This was not infinity, as rows of numbers marching toward the horizon, but infinity as a quality of existence itself, an endless unfolding, soft and inexhaustible, resisting every attempt to be confined.